I'm Dr. T. Welcome to my office. And today I'd like to talk about force. Insert Star Wars joke here. Okay, so I'm not talking about Star Wars. So in this case, previously I talked about acceleration. And of course how you kind of feel it when you accelerate. So we're going to jump into this and look at Newton's laws. And once again, picture of a cannon will be coming up over here shortly. Okay. So let's look at our cannon and let's look at the bottom. So of course you've got your cannon before you light the fuse, you got the powder and you got the cannonball and it's just sitting there. There's no acceleration on that cannonball because there's no net force. There's still forces on that cannonball. You have the force of gravity pulling on that cannonball, but there's also what's known as the normal force, and that's the force of the things under you pushing against you. So right now I'm sitting in a chair, and so I'm pushing on the chair. Gravity is pulling on me. I'm pushing on the chair, and the chair is pushing back, and that's why I don't, fall down. That's called the normal force. Since there's no net force, the two vectors cancel. In this case, the red vectors are going to be forces, the blue vectors are going to be accelerations. So since the two forces cancel, you notice two arrows, they're pointing in opposite directions. They're same size, they're going to cancel out to zero. There's no net force, the cannonball does not move. As Newton would put it, objects at rest tend to stay at rest. Their velocity doesn't change unless you put a force on them, a net force. Okay, so of course cannons, you light the fuse, psst, cannons go off, you got the gunpowder, it quickly turns into a very hot gas, and in the process pushes really hard. Now, this is going to have a couple of consequences. One, obviously it's pushing on the cannonball, and it's going to be pushing the cannonball out the barrel, but that push is also being reciprocated. It's pushing on the cannon. So if you've ever seen a cannon fired, they tend to go backwards. That's because, as Newton would put it, for every reaction there's an opposite equal reaction. So the cannonball goes out, that same force that was pushing on the cannonball is also pushing on the cannon. And that's why if you've got really big cannons, they have really big feet. They are meant to not go back too much. Otherwise, they go flying, and you don't want that. That could be worse for you than the ship you're shooting at or whatever you're using this cannon for. Okay, so we've got ourselves our cannon, and we are accelerating the cannonball. While it's in the barrel, it's accelerating. This is why some cannons have longer barrels. It gives you a little bit more oomph. There are diminishing returns. Now, of course, gravity is still working on it, but compared to a bunch of gunpowder, gravity is not much at the moment. Okay, so now it's being pushed down the cannon barrel. Now, what describes how fast it accelerates? Well, there's two key functions here. One, just how much force did you push on it? The more force you push on that cannonball, the faster it's going to accelerate. The other feature that's going to really determine how fast that cannonball accelerates is how massive it is. Mass has a property, or matter has a property known as inertia, and that's its resistance to be accelerated. The amount of oomph it takes to accelerate something. This is simply just a feature of mass. So when you describe something in kilograms or grams, you describe its inertia as well. The consequence here is that if you have a light thing, you can accelerate it much more than if it was a heavy thing. And this is why the cannonball goes out the one end really, really quickly, but the cannon just kind of goes backwards kind of slowly. Not necessarily slow, but a lot slower than the cannonball. That's because the cannon is a lot more massive than the cannonball. Okay, so now you're traveling, and now, yay. Well, you've got gravity, and at this point, even though you're not really falling, you're kind of in a free fall scenario. Really, it's more proper to think of that once you're at the top of your arc and you're falling back down. But you're still kind of in the scenario where the only force on you is gravity. You've got all of your acceleration, you've got your mass, you've got your velocity, which together, mass times velocity, is what we call momentum. And this momentum is going to be what the acceleration due to gravity is trying to overcome. And so the more momentum you have, the more gravity it's going to take to overcome that. Specifically, the longer it's going to take gravity to overcome that. Because, if you're trying to accelerate something, you can either apply more force or you can accelerate it for longer. So momentum is really a description of how much force and time it's going to take to accelerate something to the point where you would like it. And in this case, it's how much force and time is it going to take to accelerate my cannonball to stop. So remember, slowing down is accelerating. I know, counterintuitive, isn't it? Okay, so once the cannonball's at the top, gravity is still pulling on it. It's still accelerating it towards the ground. So now it's, instead of going up, the vector is going to go down, and the cannonball is going to start falling to Earth in classic free fall. Now, if we don't have air, that's the story. It makes this beautiful parabola, absolutely gorgeous math. If we do have air, though, not air, my bad. If we do have air, that will create friction. So as the cannonball is traveling, it's going to hit air molecules. And it's going to exert some of its momentum, and it's going to trade some of that, and it's going to accelerate the air molecules out of the way. They're going to rub against it. That's going to create some heat, as well as simply they're going to get pushed out of the way. And that's going to take some of the velocity away from my cannonball. It's shedding its momentum, transferring it into the air molecules. Once you have momentum, it's always conserved. So when you started out, you had a mass and no velocity. So now the cannon goes one way, the cannonball goes the other. Those momentums will be the same, just in opposite direction. And now the cannonball is traveling through the air, and it's transferring some of its momentum, some of its velocity, off to the air molecules, and therefore it's slowing down. Now, how much it sheds off? This is going to be heavily dependent on what shape the thing is, how big it is, specifically cross-sectional area, so basically, how big around is it? As well as the density of the air. If you're up high, you have less air resistance. That's why planes like to fly high. They get less drag than if they were to fly low, much more fuel efficient. You don't have to accelerate air out of the way as much, so you can use less fuel. You don't have to put as much push behind your plane. So this one gets complicated. This is one of those classic scenarios where we're going to talk about it fairly simple, but to actually do this in detailed, and if you were trying to say shoot a cannon and hit something, there's a lot more math involved than what we're covering. Now, I'd like to turn our attention just briefly to gravity. Gravity is a really interesting thing. Gravity is the attraction of two pieces of matter towards each other. And of course, the biggest piece of matter around, at least where we're sitting, is the Earth. Obviously, there's other things like the sun, and I'll deal with that later. But right now, we'll think about the Earth. So you've got mass, it's attracted to the Earth, like the cannonball. But the Earth is actually attracted to the cannonball. Just, it's a lot bigger, so it's not going to really do much. So we're going to focus on the cannonball. The cannonball is going to be accelerated towards the Earth. The force of gravity, what's causing it to be accelerated, is a function of the Earth's gravity, lowercase g, times the cannonball's mass. Now, because mass is both in the amount of force that gravity is exerting, and it's in the amount of force needed to accelerate a cannonball, the two cancel out. So look at F equals mg and F equals ma. Set those equal to each other. So mg equals ma, the m's cancel. The force of gravity is an acceleration. Things around Earth, as long as you're fairly close to the surface, will be accelerated towards the ground at pretty close to 9.8 meters per second per second. Interesting. So this has a couple of really interesting consequences. If you don't have air, if you have a nice vacuum, because once again, that air resistance we talked about is going to make a huge difference depending on what you're dropping. But if you were to drop something light and fluffy like a feather, and something dense and heavy like a hammer, the two would hit the ground at the same time. I know, weird, right? The other interesting consequence would be if you were to take that cannon, make it so it was pointing nice and flat, so not pointing up, fire the cannon, and at the exact same time drop a cannonball, both cannonballs would hit the ground at the exact same time. Because once again, if the cannon's not pointed up, gravity is only accelerating it towards the ground. It's not having to, decelerate it going up. And so, yay, interesting consequence. So with that said, I will see you next time.